Alright, welcome back. So in the last video we understood what chemical equilibrium is. Now in this video we are doing what actually comes in exams, and that's calculations. Now one thing that you should know about chemical equilibrium is any equilibrium question follows the same pattern every time. So here are the steps you should follow when solving equilibrium calculations. The first one is write the equilibrium expression. Then the second step, which will be our main task for today's lesson, is use an ICE table. Now I'm going to show you how to calculate equilibrium calculations using ICE table. Then the third step is apply stoichiometry. The fourth step is solve for equilibrium concentrations or pressures. Understand all this through an example. So the first example is we have H2 gas plus I2 gas, which is equal to 2HI. Now mind me on that equal sign. That equal sign should be in this way. That equal sign should be like this, supposed to be like this. Now having talked over that, let's try to do this example. So at a certain temperature, the equilibrium constant Kc is 49. Then we have the initial concentrations, which are there appearing on the screen. We have H2, which is 0.5, and the others. Now our task is to find what? Is to find the final concentrations using the initial concentrations and the what? The equilibrium constant. Now how do we go about it? So the first step is write the Kc expression, the equilibrium constant expression. That's our Kc expression because Hi is the product and they are the coefficient of 2, so we raise it to the power 2. Then what about the products, the reactants? The reactants, we have H2 and I2. So now after writing the Kc expression, now we go to the second step, which is the ICE table. So from today you're going to know how to use the ICE table. Now maybe you are wondering what ICE means. When we are talking about ICE table, it is ICE. So what this ICE means? I means initial concentration, then C means change, then E means equilibrium. So even when we are going to use the ICE table for initial concentrations, we are going to get the values of here, these values which are H2, which are said initial concentration. These are the values we are going to use. So this is how we write the ICE table. So what have we done? For example, we have H2, I2, and HI. So where did we get these values for initial? It was there in the previous question. It's here. We have Hi is 0, H2 is, so the initial concentrations are the ones we have just pasted there on the initial. What about change? For change, we go to the equation, the equilibrium expression. So for the reactants, we are going to see that H2 and I2, which are the reactants, they have the what? The coefficients of 1. Now for the reactants we put a negative. That's why you are seeing a negative here. For Hi, which was the product, since it's 2Hi and it's a product, products are positive. That's why you are seeing a positive 2x there. The 2 is coming from the coefficient of what? Of Hi. Now what about the equilibrium? Equilibrium, now you just do like 0.5 minus x, you get the what? You get the equilibrium for H2. So this is the value you are going to have for H2. What about I2? Same story. What about HI? 0 plus 2x, the answer is 2x. Now how do we find the equilibrium? We want the value of equilibrium, not just an expression which is 0.5 minus x. How do we find the value of equilibrium? We find the value of equilibrium by finding the value of what? Of x. Now again, how do we find the value of x? Find the value of x by substituting in the what? In the KC expression. So that's why the first step was writing the KC expression, which was something like KC. It was something like KC is equal to HI squared over H2 times I2. Now instead of writing the KC, we replace the values. So where there is KC, we put 49, because we said the equilibrium constant in the question is 49. Then where there is HI squared, we put what? The value which is there, we put this value which is 2x for what? For HI. So it's the one that we put here. So it's going to be 2x. So it's going to be 2x squared over, we multiply these two, which is 0.5 minus x. So this is the equation we are going to use to find the value of x. So as you can see, I just got the values of the equilibrium, which is 2x was the equilibrium, even 0.5 minus x. Now as we can see here, 0.5 minus x and 0.5 minus x, they are the same. So we, instead of saying 0.5 minus x, we'll just say 0.5 minus x squared. Now after doing this, as we can see, on the right side we have 2 squared, and even on the left side we can square this 49. So what do? We square 49 and we square the right side also. What are we going to have? Oh, sorry, not square but square root. So we are going to find that the square root of 49 is 7. The square root of 2x squared is 2x. The square root of 0.5 minus x is what? Is 0.5 minus x. Now, what do we do to find the value of x? The value of x, we just cross multiply and find the value of x. When we cross multiply, this is what we are going to have. 3.5 minus 7x is equal to 2x. Now, this is just algebra. So, at the end, we are going to find that when we 7 crosses the multiply, the equal sign, it will be 9x. So, it's just 9x is equal to 3.5. So, what's the value of x? Our x is going to be 0.389. Now, having found this x, how do we find the values of equilibrium? The final concentrations now at equilibrium, what are the concentrations? So we just go back to the table again. Come to the table. For the concentration, the final concentration of H2, we are going to say 0.5 minus the value we found for what? For x, which is 0.389. At the end, our value of H2, at final concentration, we'll find that H2, so same applies to I2, will be also 0.11 more per dm power 3. What about HI? HI we just multiply. So since it's 2x, so 2 times the value of x to find what? To find HI. So at the end, those are our final concentration for HI, H2 and the I2. So this is how you use the ICE table. So whenever someone talks about ICE table, just know they are talking about initial change and the equilibrium. What are the things to note there? The reactance, it's negative. Negative what? The coefficient. If the coefficient is 1, you are just going to say negative x. If the coefficient is 2, negative 2. What about the products? The products, it's what? It's positive. Another example. Now let's try to reverse the problem. Here, instead of the initial concentrations, we have been given the what? We have been given the final concentrations. We have been given at the equilibrium. So your job here, they are asking you to find the equilibrium constant. So how do we find the equilibrium constant? We write the Kc expression. So at the end, we are going to see that the Kc expression is Kc is equal to NH3 power 2. Where is the 2 coming from? The coefficient, over N2 times H2 power 3, the coefficient also. Now for this one, there is no need of using the ICE table, because you have already been given the what? The at equilibrium. Now what do you do? what you do here now is just replace where there is NH3, put what is 0.4. Where there is N2, put 0.2. Where there is H2, put what is 0.3. Place that we are going to find that our final answer will be 29.6. This 29.6 is our equilibrium constant. So here no IC table was needed because equilibrium concentrations were already what? Were already given. Let's look at another thing, which is direction of reaction. Now this is where many students usually lose easy marks. So to predict the direction, we compare Q and K. That is why I've written Q versus K. Now what does Q mean? Q means the reaction quotient. What about K? K is the equilibrium what? The equilibrium constant, which we have been doing. Now, the rules that you should know is, if Q, which is reaction quotient, is less than K, then the reaction moves forward. What about when Q is greater than K? When Q is greater than K, reaction moves what? Backward. What about Q is equal to K? It just means that equilibrium, it is at equilibrium. So this is how you know the direction of reaction. So they will be asking you, predict the direction of reaction. Or they can say, is this favoring products or is this favoring reactants? For example, when the reaction moves forward, it means products are being favored. Here is the example. We have CO plus H2 is equal to CO2 plus H2. As usual, that equal sign, it's supposed to be like this. Yeah, meaning that is the one that's showing equilibrium. So we have the current concentrations they have given you, and also they have already given you what? Kc, which means you have equilibrium constant. Now the constant that we are going to calculate using the equilibrium constant formula, you are finding Q, which is what? Which is the reaction quotient, which you are going to compare with what? With Kc. Now, as you can see, I've already calculated it there, which is the products CO, which is 0.5 times 0.5 over 1.0 times 1.0. The answer is 0.25. Now, if you can compare this 0.25 is less than the 4, which is for equilibrium constant. Just as I said, now this Q is less than what? Is less than K. And when Q is less than K, it means the reaction moves forward, forming what? More products. So that's how you are going to be calculating, knowing the direction of the what? Of the reaction. So always they are going to be giving you the equilibrium constant. Now the concentrations, you are going to use them to find the reaction quotient, and after that compare the reaction quotient with what? With the equilibrium constant. Here is another example. Just as I said, the equal sign is supposed to be what? It's supposed to show two arrows. Another one going forward, another one coming backward. Now, this one, it's a very easy but dangerous exam trap. What's there is they're going to say, can you show the equilibrium concentration, the equilibrium expression in terms of equilibrium constant? So the formula of equilibrium constant here, as you can see, calcium carbonate is a solid, which is equal to calcium oxide, which is also a solid, plus carbon dioxide, which is a gas. When you are writing the Kc, we said it's what? Products over reactants. So the products, we only write CO2 because it's a gas. Also the reactants, we can't write calcium carbonate because it's a solid. So at the end, we are going to end up with the Kc expression as CO2 only, the one I wrote there. So what should you take note here? You don't write the solids in a Kc expression. So that's the end of our lesson today. Here is, let me just leave you with this summary, which is IC tables win marks. Also follow stoichiometric coefficients. Compare Q with K before guessing. Ignore solids and pure liquids. Show full working. Chemistry is method based. So this is the end of today's lesson, and in the next lesson we are going to talk about Lee Cartelius principle with what, with the calculations, and that will be the end of the end topic in what, the end subtopic in chemical equilibrium. So thank you for watching, and don't forget to like and subscribe. Also share to your friend or a classmate. So see you in the next video.